Okay, so yeah. Anyway, I might as well get started, I guess. So basically tonight I got one more. So I got one more to do with the integrating factors. We're doing exact equations. You might remember a couple classes ago now, but we're doing integrating factors, exact equations. I got one more of those to do tonight, and then we're basically done with the chapter 2. So we're all done with that. Then we'll go on to the next chapter. But anyway, kind of picking back up where we left off, sort of. It's like section 2.6 kind of continued here. They were called integrating factors. Okay, and so we had, here's an example. So here's a differential equation. Kind of a messy thing here. Let's see. Say D, or try this again here. Okay. So let's see what this differential equation here, right? And this is not exact, okay? It's not an exact equation. Okay, and then a couple of things here. So first I want to do, try to make it exact by finding the integrating factor. Okay, find an integrating factor. Okay, and we're also going to assume here that x is greater than 0 in this. Okay, let's see. So just to recall, what does it mean to be exact, right? If this thing here, if this is like the partial respect to x of something, so if this is partial respect to x and if this is partial respect to y of something, okay, then it's called exact, right? So if this is partial respect to x of something, partial respect to y of something, then it's exact here. But it's not exact here, but we'll find what's called an integrating factor, okay, to make it exact. And one way we could do that, okay, to help find an integrating factor, you figure out this quantity here, right? So actually, let me move this down just a bit here. Okay, so you want to find this here, right? So you find m sub y minus m sub x over m, like that here, where this is the m. Remember, this is the m, right? And this is the n over here, right? So to help find an integrating factor, okay, figure out this quantity here, m sub y minus m sub x over m. Okay, so that'd be equal to what here? Okay, so how would that go here? So you gotta find m sub y. Can somebody tell me about m sub y? What would that be? So partial respect to y here. Right, 45x squared y squared, right? So 45x squared y squared, and then partial with this with respect to y would be 30y, right? So 30y, so plus 30y. So we got that. Then minus, so that's that one, and then minus the n sub x. So partial with respect to x would be what? That is 27x squared y squared, right? Yep, 27x squared y squared. And then n sub x here would be what? That'd be 10y, right? So plus 10y. Good. Okay, all divided by m, which is this thing over here again. Let's get this here. Okay, and now what we're looking for here, to find an integrating factor, right? This thing has to be a function of x only. Okay, so if you simplify this out here, okay, simplify this down, if we try to here, that gives what? It's a mess here, but you get like, so 45 minus, you got like terms here going on kind of. So it's like, 18 x squared, y squared, I think. And then for the y's, it would be, you got 30y, subtract 10y, would be 20y, right, over, so it's atrocious here, actually, 15x squared, y cubed plus 15 y squared, like that. Okay, it doesn't look promising here, actually, but wait a minute, wait. Oh, my bad. I'm sorry, I messed this up. This should be an n. This is supposed to be an n down here. For this integrating factor check, okay, this is supposed to be an n. I got my formula wrong. This is an n down here. So then this guy here, sorry about that. This is now 9x cubed y squared plus 10xy. That was looking so good there. Yeah, this is the formula here, like this. Okay, and if you, it still looks like a mess here, but if you factor this out, right, there is a common factor numerator here. You can take out like a 9, or yeah, you're right. Why did I say 9? 2, right? 2y actually. You can take out 2y there. That leaves, I gotta be careful, 9x squared y plus 10, I think. Right, and then down here, you can take out common factor here of a y or xy, I believe. And that leaves behind what, 9x squared y plus 10, like this. Okay, and you notice here there's actually nice canceling. These cancel here. Okay, and then also the y's would cancel here. Okay, that were brought out. This is equal to 2 over x here. Okay, which is obviously it's a function of x only. Okay. Okay, which is good. Okay, so that's good here. So that's a function of x only, which means then that we actually can find an integrating factor for this. Okay, remember integrating factor then, oh yeah, so next thing, find integrating factor. Okay, so it does exist, and this is a function of x only. Then the integrating factor, okay, would be this. I think I used the letter, I use a letter for it, maybe U for integrating factor. Yeah, so okay, so then integrating factor is, okay, it's u, I'll call it u equals, it's e to the negative, I think there's a negative on it. No, actually, I'm sorry, there's no negative on it. E to the integral p dx, or not p dx, but the thing you get here, which is 2 over x dx. Okay, equals, and that's e raised then to, and then this guy up here would be what? So integral of 2 over x. So that's like, yeah, 2 ln x, right? So that's 2 natural log absolute value of x. And I mentioned here that x is greater than 0 in the beginning, right? X greater than 0. So basically, I can drop the absolute value off of there, and you turn that, you do some stuff there. That's x squared. That becomes x squared right there. Okay, so that's the integrating factor. Okay, now what do you do with that? So if you take the original equation now, right? So if I go back up to the original, multiply through by the integrating factor. Okay, so I guess I got to rewrite the original here to see it. I got to write it down again. So 15 x squared y cubed plus 15 y squared dx, right? This is the original here, plus 9x cubed y squared plus 10xy dy is equal to 0. That was the original problem there we were doing. Okay, and now the integrating factor, you multiply through by it. So you multiply through by integrating factor all the way across. So basically, it's like multiplying through by x squared here on this. Okay, so then that becomes what? 15 x to the fourth y cubed plus 15 x squared y squared dx plus, then by x squared over here, that's 9x to the fifth y squared plus 10x cubed y dy equals 0. Okay. This is now exact. Okay, this is an exact equation. Okay. All right. So anything there so far? Now remember, once it's exact, okay, then there's a thing you can do here. You identify this. This is like your m here now, right? So, or actually, yeah, I don't have to use the m and n here really. This is like the new m. You can think of like the new m, the new n here now for our new problem for this new one now. Okay. So this is m and n, or m and n here like that. Okay. So now, basically, what you do here then, this is the part. We're looking for an f of x, y now, okay, for this here. Yeah, so you have, so this now, right? So since, I'll say here, since exact, right, m is equal to the partial f with respect to y, or with respect to x, I'm sorry, and n equals partial of some function with respect to y here, okay, for some f of x, y. Okay, so now we got to figure out what this f of x, y is here. Okay, so then basically this is the m here. So you have f of x equals 15 x to the fourth y cubed plus 15 x squared y squared, because that's the partial with respect to x. So now what you'll do here, you take antiderivative now, right, with respect to x of this. Okay, so then that'd be what? F of x, y. So basically take antiderivative with respect to x here now. So that would be what? How would that go? So antiderivative with respect to x. Right, this is x to the fifth over 5. So 3x to the fifth y cubed plus, and then partial, or then antiderivative here would be, that'd be 5. Because you take part, so it'd be 5x cubed y squared. Right, plus some function here. I use something here. What do I use for that? I used a phi, maybe like that, plus some function of what y here then, like this. You get this here. So you take antiderivative with respect to x here, you get this. Okay, but okay, and you can check if you take the partial of this with respect to x, right? You would get this back here, hopefully. If we did that right. Okay, get this here. Now, next thing then, so f of x, y that we're looking for has to be a function like this here. Now, you take the partial of this now with respect to y, and I hope this works. Okay? I didn't work this problem all the way through. I hope it cancels out. So partial with respect to y would be what here now? That would be, so go through respect to y. That would be what? 15 x to the fifth y squared. Like that. With respect to y, right? So that would be, yeah, 15 x to the fifth y squared. I hope this works. I mean, this isn't, okay. And then next one would be, well, it's got to work now because it should work. And then this is what? This is partial respect to y. That would be 10x cubed y, like that. Okay, plus, and then some function of y over here, like this. I don't know. Doesn't look very good to me. Let's see. Let me check. Now, what should happen here then? Okay, if I put partial respect to the f sub y here, I put that over here. Oh, we're good. We're good.
Would that be a prime on that?
Oh, yes, this would be. Actually, it's okay. We're good here. Okay, I think we'll be okay. Thank you. It is a prime. It's a prime one there. That's right. Okay, now the f sub y, then that's this over here, right? So because f sub y is the n over here then. So then that would give me what? I get 9x squared, or I'm sorry, 9x to the fifth y squared plus 10x cubed y equals 15x to the fifth y squared plus 10x cubed y plus some function here, phi prime of y, like that. Okay, and this is good. These cancel, right? So let's go there. And then I get, I get not, and then I get what? 9x to the fifth y squared equals 15x to the fifth y squared plus phi prime of y, like that. And why aren't these canceling? I want the x squareds to go, or the x to the fifths. Shouldn't have any x's left in that. I thought they were canceled, but not as long as this is over here. Let's see. May have miscopied something. Let me go back. Let me look at this carefully. We may be on this while tonight. 15x squared y cubed. That was the original. Let me make sure I copy that. 15x squared y cubed, 15y squared, 9x cubed y squared, 10xy. Okay, and we did the exact thing, right? And we got this is our integrating factor. It can't be a mistake here, I don't think. That X. Well, let's see. Integrating factor x squared. Let me go through this here. That's that. Maybe I messed up the antiderivative there somewhere. Let's see. Here, you mean? Okay. Well, it's a partial respect to antiderivative respect to x. So that would be x to the fifth. Fifteens on there. Apparently, I got this here. I got an integrating factor, so that makes it exact at that point. And I multiplied through by it. Did I multiply it right or something? Let's see. I didn't work the problem the whole way through before I started tonight, but I thought it should go okay. 10xy. That is m sub y. Two over x. And that's what I got before when I did that. And this has got to be x squared then. So I'm pretty confident up to there. That should be right. And then did I miscopy it when I brought it down? It's 15x squared y cubed plus 15y squared, 9x cubed y squared plus 10xy dy equals 0. I went through by the integrating factor. So through by x squared. So I should tack on 2 here, there, and there. Now I could do a check here. One thing I have to check. Is this really exact? I said since it's exact, but if I take partial respect to, I'll find out something here if I do this. Wait a minute. Move out of the way. So if I take m sub y, that is what? That is, go through that. That would be what? 45 x to the fourth y squared plus 30 x squared y. That's m sub y, right? And then n sub x, because mixed partials have to match. That would be 45x to the fourth. Okay, 45x to the fourth y squared. I'm doing n sub x here now. And then plus 30x squared y. Okay, so that matches. So we're good to there because that's good. Okay, so then this, okay, now I take antiderivative with respect to x. So this would be, I think that would be right. That looks okay to me. And then antiderivative with respect to x is here. Be that plus a function of y. Now I'll take partial respect to y. That would be 15x to the fifth y squared plus 10x cubed y. I'm not sure what's going to happen here. Plus that. Oh, wait a minute. I know what it is. I think. Did I? No, this is exact. So I multiplied through by it. So I copied this down right here. Okay. I'm using this one now, right? Is this exact? Okay, so f sub y, or I'm sorry, so f sub y is this. So 9x to the fifth plus 10x cubed y equals oh, let's see. So 10x cubed y. Okay, 9x to the fifth y squared, 10x cubed y. That's that side. And this side is this. But I can't get rid of x to the fifths there, though, I don't think. Or they're like terms, I guess. I can do that. So, but that doesn't get -6, -6. I can collect them all to one side, but -6x to the fifth y squared is 5 prime of y. But there should not be an x in that. I may have to come back to that. Does anybody see mistaken anywhere? Am I looking through it? This should only be a function of y. It shouldn't have an x in it. I thought they were going to cancel nicely here, but the x is not going to go away there. Let's see. Well, if you guys come up with something, let me know, and I'll work on it. I'm going to work on that, okay, and see what it is. But there's something not quite, I'm missing something in that. I'm not sure what it is. Because I know this is exact here now, right? This is exact. So is this an exact equation? Right, this guy here is exact. And I did the cross check there in that. So that's f sub x, f sub y. Yeah, I've been through that a couple times now.
I am getting kind of confused.
Yes.
When you said, since it's exact, equals f sub x, and then you wrote f sub x equals 15x to the fourth.
Yeah.
But you also have n equals f sub y, but in f sub y.
This is the n.
Right.
Okay.
Why didn't you just copy 9x to the y squared?
Oh, did I? Wait, here?
No, underneath your
oh, okay, under here. Like, okay, so I took the partial here. Did I pick the wrong one of these maybe to, let's see. Wait a minute. Okay, so this was, okay, this was the f sub x was this. this one here. This is the exact one here. This one's exact. So this is the m here. And you take n with respect to x. Apparently it's this. Oh, is that a 3 here? Is that a 3? Oh. Okay, maybe there might be hope. I didn't do that right. This is a 3 here, not a 5, right? Is that right? Is that right? You guys gotta make sure I'm right. That's a 3 there, right? And then now over here, is it the same, or that's a 3 there? That's a 3 there, and then this would be this is a 5. This is a 5.
Remember I said that earlier.
Okay, you might have said that. Okay.
No, I said the mistake was somewhere right.
Okay, yeah. You're right. Okay, so that's a 3. Okay, you're right. Okay, now, still hope. Okay, and then now I think the rest of that's okay, right? Yeah. Yeah. Okay. Now I take the respect to y, so that makes now 9 here. Is that right? And then this hopefully is okay. Yeah, that's better. Okay, and then we got that. So okay, yeah. So now I copied that down here, right? Left side from back up here now. Okay, that the left side is this. Okay, and now the right side, corrected right side is this here. Right now they all cancel. Okay, that's better. Thank you. Yeah. So those all cancel there. So basically, these two lines are gone. Man, that's that 5 to 3. That was the. And then, thank you. So now I get this, like this, okay? Which means then that, yes, that means phi of y here is just a constant. Okay, so you can call it k if you want some constant here. Okay, so you got that. So then the solution of the whole thing, right? It's f of xy equals c. So f of xy, that's this part here. So 3x to the 5th y cubed plus 5x cubed y squared plus, and this thing here is a constant, k, or actually you can call it 0 if you want, it doesn't matter. But then this is equal to c over here, some constant c, like that. And, but the k can say 0. So actually, you could just, or move the k over to this side if you want then. So you get 3x to the 5th y cubed plus 5x cubed y squared equals c, a constant. Okay, so that's the solution then to the differential equation. It should be this one here. You go through the whole thing. Okay, and so any questions on that one? Stumbled through it, but yeah. So that was the last of the exact. We did some of those before, some of the exact equations from last time. That was a leftover one I didn't get to. So I wish I never got to it actually, but anyway, yep. But thank you for all the help correcting it there from everybody. So yeah, it was this guy right here. It should have been a 3, not a 5. So okay. Well, yeah, I've got that. So okay, let me see here. I'm kind of curious to see on GeoGebra what it looks like. That'll probably kill like a 15 minutes here, but I'm curious though. I'm afraid to check it. Well, no, we should be okay because we've made all the right steps along the way now. So we'll see what we got. So I'm going to exit full screen here for a minute. I want to share this. This is going to kill a bit of time here. I probably don't need doing that because then you get to the next chapter. But okay. But anyway, stop share here. Let me share some Desmos. I want to go to GeoGebra. See if we can figure some of this out. GeoGebra.org. Okay, and share the screen here. Okay, I want to do slope field. I'm going to get a slope field for this thing. So slope field, just draw the slope field for the differential equation equals, how would that go then? I should probably, what was the differential equation? The original one, it had the stuff with dx plus stuff with dy equals 0, right? So you would, if you move things around there, if I divide through by dx basically, and then I would move the top over to the right then. So basically, I think it's going to be like this. Here's another place I'm going to mess up, but y cubed plus 15y squared. So if you divide that thing through by dx on both sides and move over, and then that'd be your numerator like that, and then you would divide, or slope field. Wait a minute, I want slope field of. I need to open a parenthesis here. That divided by, now the thing in front of the dy was this other piece then, 9x cubed y squared plus 10xy. So this is differential. This is like the right side. If you say dy dx equals, right, this would be the right side of it here. Okay. If you divided that thing through by dx and then move things around, get dy dx equals, okay, it should be this here, I believe then. I'm just going to double check that before and then, yeah, okay. So then there's a slope field apparently like this for the differential equation. Now let's just take our curve, one of our curves. Our solution curve was, well, I never solved it. Did somebody tell me what was the solution thing at the end? The f of xy equals, did anybody write it down? The f of x, what it was? Well, I can go look for it at the end. So our final solution there at the end of the thing is 3x to the fifth, 3x to the fifth y cubed plus 5x cubed y squared, I believe. Is that right? 3x to the fifth, is that what I wrote? Okay, equals c, so a constant here. There's our constant. And now if I make a slider here, well, I can just get some of the solution curves. Yeah, it matches up. So kind of a mess here, but it's kind of a complicated thing. But the solution curves, they do match up here. Got some strange things going on with it, but it looks like it matches up pretty good with the slope field everywhere on it. So I think about some of the solutions there. So I'll just pick one here, for example. Let me say equals 10. Yeah, there's one solution there, for example. So it actually worked in the end there. That's the solution, one of the solutions there. Or if, say, maybe pick, say, like another number, like 6 or something. Yeah, so let's say we got solved. And so, okay, switch back here. Share screen back. Next chapter here, actually, I think it's a little bit easier again the problems get a little bit shorter, maybe here. Yeah, okay. So we'll go a little bit into this now. So these are like some application problems with differential equations. So we're going to skip chapter 3 for now and go on to chapter 4. So we'll kind of get started here. So chapter 4, and we're not going to get through all this tonight, but here's some applications of first order ODEs, ordinary differential equations. Okay, and we're going to start kind of a simple or an easier one here, and then we'll get fancier as we go. Let's say we have this here. Right, so suppose the number of bacteria in a dish is governed by, so it's like a model here for it. Let's say, and number of bacteria B is like number of bacteria here. dB dt is equal to KB. Okay, so number of bacteria B. So B is like the number of bacteria and T is time. Because number of bacteria is a function of time in a dish, like in a petri dish or something. Okay. So it's given, let's say it's supposed it's modeled by this here. dB dt equals KB. Basically, the more bacteria in a dish, the faster the rate of changes, or the more they grow, the faster the population changes, right? So the rate of change number of bacteria is proportional to the number of bacteria there. Okay, and so, and let's suppose also here, suppose at time 0 there's 1 bacteria, so B of 0 equals 1, and let's say B of 5 equals 100. Okay. The time might be in days, hours, minutes, whatever. Okay, but let's just say this is the, so at the initial time there's 1 bacteria, and then 5 hours or 5 weeks, whatever it is, 5 later, say 5 days later or 5 hours, there's 100 bacteria in the dish like this. Okay, and the question is here then, we're going to find this here then, find the number of bacteria as a function of time, find B of T. So basically what we're doing here, we're solving this separable differential equation. We have this K in here though, this constant, but we're just solving the separable differential equation here. Okay. It's also linear. It's also a linear differential equation. You can do it that way, but we'll do separable. Okay, but so if you solve it here, we'll do it by separation of variables. So how'd that go then? Basically, you get 1 over B dB is equal to what, K dt, right? So if you separate it out, you would get this. Okay, and at some point we'll find the constant. Okay, we'll figure out what that constant is here as we go. So now I do antiderivative both sides. So left side would be what? Here, that'd be natural log of, we'll assume just B here. We'll assume B is greater than 0. No negative number of bacteria. So we'll assume B is greater than 0 here. So that'd be natural log of B on that side equals, and then this side would be what? Antiderivative on the right side? KT plus C. Right? Don't forget the plus C there on that. So when you do that. So KT plus C. Okay. So then you go through this here, and basically if I put the E under both sides, I get B is equal to E raised to the KT plus C, like this. Okay. And then you do some exponent rule stuff there. But basically you can turn it into this then. B is equal to some constant times E to the KT, like that. It's a different C there. I changed the C midstream there on that. But okay. So anything there so far? That. Now, what we have to do here to finish the model, then we got to find the C and the K in this. Okay, so we can use these conditions here to help. So, so how'd that go then? Well, what about at? So we got to find so we use initial conditions here now. Okay, so let's say, so I'll say here now. Now apply the conditions. Let's now apply the conditions here. Okay, so if I do the first one here, what, when T is 0, B is 1, so I get this. Right, so when T is 0, B is 1, you get this here. So that means what then? C is equal to 1. So we got that. Okay, so now we got what? We got that B is equal to basically just 1 times, or just basically can say E to the KT. It's just 1 there, we got that. Okay, now apply the other condition. Okay, so the other condition then would be what here then? That would be B of 5 is equal to 100. So I get 100 equals E to the K times 5. So 100 equals e to the 5k. Now solve for k, then what you do? Take natural log of 100, take natural log both sides. So natural log of 100 equals 5k. Okay, so then k is equal to natural log of 100 divided by 5. Like that. So then finally, right, the model would be this one, right? It'd have b equals, it'd be e to the natural log of 100 divided by 5 t. Because now we got the c and the k here now. In that, right? So this would be it here. So this would be number of bacteria then as a function of time would be this. So it's like exponential growth growth there. Okay. Or actually, it's a growth, exponential growth. Yeah, on this one. Yeah, that's right. So yeah. So basically, if I were graph it in Desmos, right? If I graph it on a computer, right? Basically, like say here's T and B, right? This would be say at time 0 is 1. The graph would go like this, right? It'd be number of bacteria. It'd be increasing like this if you were to graph it out. Okay. So that'd be it there. Anything on that? And see if I look at the slope field, right? If I look at the slope field for the differential equation, let me stop here real quick. Stop sharing here. Go to the slope field here real quick. Go back to the GeoGebra. Get rid of all this stuff here. So what we got here? We got I got to use y, and it doesn't use b, and you have to use y and x. So slope, it'd be slope field. Now it was the differential equation. It was KB, right? So now the k, I got to put the k in here, I guess. The k was what, natural log of 100 divided by, what was it? Natural log of 100 divided by the k, by 5, was it? Okay. So, and then I'd have b here, or y after this. Right, so I guess that'd be it. Right. So here's the slope field then. It looks like this for the model. Okay. So if you have different initial conditions here, you can see the growth then. So for instance, our initial condition, there was one bacteria initially. So at time 0, there was 1. And then the solution was what? It was y equals e to the e raised to that k again. So I guess I'm typing it again. Natural log of 100 divided by 5, divided by 5, and then I got to put x here, I guess. There it is. So this would be the growth of the bacteria then. It's like exponential growth, like that. So you got the slope field for, this is the slope field for differential equation there, and then this is the solution curve for it, the green one there. So, okay. So anything on that? So let me switch back here. Okay, and back to this. Okay, now, okay, that's actually a pretty simple model there. Okay, is this, the bacteria keep growing and growing and growing, but let's change the problem just a bit here. Okay, and this is be a more complicated model now for it. Let's say here, same thing again, or kind of the same dish. Let's say now, so it's like a new problem here. Suppose the dish can only hold 8,000 bacteria and the rate of growth slows as the bacteria become crowded.
This would it necessarily be a decay?
Well, no, not necessarily.
No,
It will be at some, it kind of is. We'll see how it goes here. We'll see if we get through this tonight, but yeah. Okay, but
Because big growth slowing down doesn't necessarily indicate
it doesn't mean they're going away. It just means there's not as many. They're not growing as fast. There's not as many.
the rate of
The rate of growth is slowing, right? That's all that means. But there's still more than there were before, But there's yeah. Okay, so suppose this can hold 8,000 bacteria, and the rate of growth slows as bacteria become crowded. Okay, now the model here you could use for something like this. So we have again dBdt. I'm going to write KB here again like this, for example. This is what we had before. Okay, but now to account for the fact that so the rate of growth slows down to get more of them. Okay, you can put another factor here like this then. Like this. Okay, so we'll kind of see if this makes sense at all. So basically what happens here, right, in the beginning, think about when B is close to, think about what happens, say, when B is 1, like when B is close to 0. So when B is, say, 1, what happens here? Basically, this is like, basically about 8,000 here, right, when B is 1. Okay, plus you got the K out there too. But so this is a pretty big number right here, when say B is 1, right? So they're growing pretty quickly when you have 1 bacteria. But what happens when you get, say, okay. It starts off slow because there's not many to start with. Okay, but as you get, let me say it this way: as you get closer to 8,000, what happens when B is 8,000? Let's say it this way: when B is 8,000, what's the rate of growth? If B is 8,000, it's 0, right? Because that's the capacity of the dish. 8,000. The growth is there's no more bacteria. They're not multiplying anymore, right? Because they're all crowded together.
They're not multiplying
because it's all crowded. They're all crowded together. They're not happy anymore. They're all crowded together, and there's not enough resources or whatever for them to eat to multiply. Okay, so so when it starts out in the beginning it's slow because there's not many bacteria to work with, right? It goes from 1 to 2 to 4 or whatever. It's slow in the beginning, and midway through it's pretty fast because if you have, say, 100 here, you take 100 times 7,900. It's a pretty big number. But again, when you get closer to the end again, we get closer to 8,000. Now it's slowing back down again. Okay, so so something like this would kind of account for that. This kind of model where you have these things multiplied together, like you have this this is like the growth slows down. This makes the growth slow down. This is called this kind of form here. It has a name. It's called logistic growth model. Logistic growth model. It basically accounts for crowding. It accounts for crowding there in it. Okay. Now let's suppose here a couple things. Let's suppose again we start with 1 bacteria. So B of 0 is equal to 1. Okay. And this time a little different initial condition here. I suppose that's equal to 1, and also suppose that wait, did I change my note up? Wait a minute. Oh, yeah. Let's suppose B0 is equal to 1. And let's also say here that, okay, dB dt evaluated at t equals 0 is equal to 2. Yeah, like this. Okay, what's this mean here? So it means you start with 1 bacteria at time 0, and this tells you about the rate of growth at time 0. dB dt, that'd be at time 0. This is the rate of growth at time 0. So suppose we're given 1 bacteria and we're given initial rate of growth, like this. Okay. Now, basically what this does, this allows you to find the K, because if you know, so at time 0, okay, when there's 1 bacteria, okay, so basically you can find the K right away. So we'll start working on a solution here for this. Okay, the K here you can get right away, actually. You can get K right away for this, right? Because what's at time 0? What goes here at time 0? What goes here at time 0? 2, right? Because dB dt evaluated at time 0 is 2, let's say. So 2 equals K. Now, what's the B at time 0? 1, right? Because there's 1 bacteria initially. And then 8,000 minus 1, right? So you can solve for K right away. So it's actually nice when conditions given like this. You get the K right away in it. Okay, so then K is equal to, basically it's 2 divided by 7,999, like this. Because that's the K here in that. Anything there so far? Now we have the K, right? We know what the K is here, but just for, I guess, sort of convenience, I don't want to drag this number around everywhere throughout the rest of the problem. So I'm going to leave it as K for now, but at the very end of the problem, we know what K is. K is this. Okay, so it's easier to leave as K for now. We'll go through the rest of this instead of dragging that number around because it's less to write. So I'll say here, easier to leave as K for now. And by the way, our goal here, I didn't write it down. Our whole goal here is this. We want to find B of t. We want to find this function here. We want to find B of t. Okay, what would that look like? Okay, so that's our goal in the problem here. Okay, so now we're finally ready to start it now. Okay, anything there so far? Okay, so we got the value of K already. We know what it is, but I'm just going to use the letter K for a while here. Now this equation up here, so let's start working the equation now. So I'll kind of write it back down here, right? We got dB dt. We got to solve this differential equation equals KB times 8,000 minus B, like this. Okay, so somehow then we got to try to recognize this as one of our things we know how to do. This is actually separable. Okay, it is actually, you could separate it right away. Okay, but actually there's a nice way to do it, I think, than use the fact it's separable. Because if you separate, you got to use partial fractions and stuff to do it then. Okay, like don't write this down, but for example, all right, you could write it right away like this. Don't write this down. We're not going to do it this way anyway, but you could separate it like this right away, right? You could separate like that because this is all a function of B here. You could divide it over and you could do that. And you'd have to do like a partial fractions here or something to go through this. Okay, but a better way to do this one though, instead of looking at separable, I think it's maybe easier. Go ahead and multiply it out here, right? So we get what dB dt is equal to K. I guess I'll say 8,000. Try it this way: 8,000 KB minus KB squared, like this, like that. Okay. Now, if I move this over to the other side, take this term, move it over to left side, I get dB dt minus 8,000 K, minus 8,000 KB, I should say, is equal to, and then that would be negative KB squared. Right, so I took this here and moved it over to left side, and then I still have this thing on the right side. I took one term, moved it over, and then the other term on the right side. Okay, anything there so far? Now, kind of a thing here. If you look at this equation, you can identify what kind of equation this is. We've actually dealt with this already in the course. Does that look like a familiar kind of equation there?
Linear.
It's not. It's actually not linear. It's not homogeneous either. Does that look kind? Say again. This is a Bernoulli. Yeah, this is like a Bernoulli equation. Remember before we had y's here before, right? And y's and x's, right? But it was like you had a something like this, and then you had like some function of x here. It was, I think, and then the y. This is actually a Bernoulli equation, the form of it. Okay, so notice here, that's the key on this. Notice this is a Bernoulli equation. Okay, so this is a Bernoulli equation here. At that point, good. Anything there so far, Nat? So you have what you did was on the last test. You had to do one of those, right? So that's a Bernoulli. So now we know how to do a Bernoulli, right? We had a whole process for that. So if you remember how that goes, if I can remember it now. Oh yeah. Basically, look for solutions of the form, and it had right. So look for solutions. Or basically, look for what do we say? Look for y equals. Well, I guess I gotta say b here. I gotta watch my letters. This b equals, there's a u, right? It'd be some function of t here, but u e to the, it was a negative integral. And then what was the part one up here? It was this part here, wasn't it? In front of this. So that would be negative, that'd be what? Negative 8,000 K, like that. And then it'd be a dt here then, like this. So we're looking for solutions like this, of this form. Before it was like x's and y's, but same idea here. So then this is what? That's u times, and then this becomes what's this? That's 8e to the 8,000 kt. Is that right? Yeah, so we'll go look for solutions like this. Okay, anything there so far? Okay, now so you sub that into the differential equation here. So now sub into the diffie q. So sub in the equation. So now there you got to use the product rule. You take the derivative, right? So you get u prime. You keep the second part. Okay, plus, and this time you keep the first part and multiply by derivative of the second part, which would be what? So derivative of the second part, that'd be e to the 8,000 kt, and then by chain rule, that'd be what? Times 8,000 k. Okay, so that's dB dt. And then minus, then 8,000 k, and then the b was what? The b was this again. Right? And then equals. And if we did this right, by the way, right, this should cancel. There's kind of a check built in, right? So I need checks tonight, definitely. This cancels here, is that right? That cancels. So those two cancel out there. Okay, and then on the other side, then what? We get negative k times, and then what's the b? The b is this again. That's the u e to the 8,000 kt. But now that's squared here. Okay, I'm going back to looking back at this. Got a lot there, but that's what it looks like so far. Anything there so far on that? So we substitute, right? We substituted this into the differential equation up here. Okay, and that gives you this. And you notice you get the cancellation here. Okay, if you're really confident on these, okay, you could actually just do half the product rule and then assume he's going to cancel. Okay, and then just have this over here if you're really confident. But otherwise, you kind of lose the check though if you do that. We still have the check here because it was actually canceled. Okay, but anyway, so what we've got now, we got u prime e to the 8,000 kt is equal to negative k. How am I doing here tonight? Can I get through this? I think maybe I can do it. Okay. And then now over here, that's k. Now what's this? And that's got to be careful. This is u squared. And then that would become, I think, 16,000 e to the 16,000 kt, like that. By exponent rules, right, the two would go here, and then it would go here. Anything there so far? Okay, and now what? Now this is separable. Actually, I can move the e to 8,000 kt to the other side. So that becomes u prime equals negative k u squared e to the, I think now when you move that over, it's like you multiply by e to negative 8,000 kt. You subtract exponents then. So you get 8,000 kt over there on that. And then this becomes then, you separate it out. So it's like du dt is equal to negative k u squared e to the 8,000 kt. So when you separate it, then you get what? I guess you get 1 over u squared du is equal to negative k e to the 8,000 kt, like that. Then you integrate both sides here. Okay, and now what? So that's u to the negative second. So that becomes u to the negative first over negative 1 equals negative k. Now, antiderivative here, and this is dt over here. Antiderivative of this would be what? That would be, it'd be, yeah, it'd be 1 over 8,000 k e to the 8,000 kt. Right, that I took the k out of here, and then antiderivative of this would be like this here. Remember, the k is just the constant there, and then I got plus c on here somewhere, plus c, like that. Okay, if I go through by negative 1, then, and the k's will cancel it. So if I go through by negative 1, I get what? U to the negative first is equal to that, and the k's cancel here actually. So then I would just get, I think, 1 over 8,000. It'll be positive now. E to the 8,000 kt plus c. You see this? Okay, and that's reciprocal of u then, right? So, you guys should double check me. Does this seem reasonable so far? Okay, let's have somebody there to make sure. Okay, and then now, so then u is equal to, right, that'd be 1 over this stuff here, 1 over 8,000 e to the 8,000 kt plus c, like that. So that's the u here then. So then finally the b, so that's the u. So what? So b is equal to, now I can't remember what was b is equal to what? Up here it was b equals, here, right here, u times e to the 8,000 kt. Okay, so now I'll say here, maybe I'll say it this way, I'll say recall, right? B is equal to u e times e to the 8,000 kt. Say recall there. So then, so I'll say here, so then, right, B is equal to, and that just go up in the numerator here, this part basically. So that'd be like e to the 8,000 kt over 1 over 8,000 e to the 8,000 kt, and then plus c. Okay, so end up with this here then. Okay, so anything there so far on that? Now remember, we know the value of k already. We'll look at that in a minute. Now also, we got to get the c from initial condition. Okay, and your initial condition here, I think we about do this. So now apply the initial condition. So now we need to get the c here now. So we've got what b of 0 was what, equal to 1 originally. Okay, so how'd that go then? So that means I'd put 1 here is equal to, now what would go here then? That would become, if I put 0 here, that'd just be 1 up here. Put 0 here, that's 1 over 8,000. Then plus c, like this. Okay. A bit of a mess here. I guess if I multiply up and down, well, I'll just multiply it over. I'll make a mess of this probably. But I'll multiply this over here. So I get 1 over 8,000 plus c is equal to 1. Right? If I take this, multiply it over. So c is equal to, it's 1 minus 8,000, 1 minus 1 over 8,000. So that'd be 7,999 over 8,000. Like this. Is that right? Or did I get that wrong? Well, no. B, it's this. Like that here. Yeah, so then C is equal to 7,999 over 8,000 here. Like that. Okay. So finally here, put this all together. Well, I could probably multiply through my 8,000 at some point, but I'll get that here in a minute. Almost done with it. See at this? Okay. And it might be nice to multiply through by 8,000, I think. So then B is equal to, that'd be 8,000 e to the 8,000 kt over e to the 8,000 kt plus 7999, or one too many nines there, like that. So that'd be made a little nicer way to write it. I don't know, like that. Where, remember K in the beginning, where K is equal to, what was K? K was 2 over, was it 2 over 7999 or something like that? I think that was the K. Okay, in the beginning of the whole thing. And so, okay. Yeah, and I was going to say another way to write it too. One other way to write it, if I multiply up and down by e to the negative 8,000 kt, you can also write like this. Maybe another nice way to write it. You can say 8,000 divided by, that'd be a 1 here, plus 7. This is probably the best way to write it. Like this. That's probably the cleanest way to write it. Like this here. So basically, I went up and down here by e to the negative 8,000 kt on the top and the bottom. Okay, and then it becomes like this here then. So if I go by e to the negative 8,000 kt up here and down here, like this, and then so if this becomes 1 right here, and then you distribute it down here, and it basically turns into this. Okay. Any questions in that last part? Do you guys follow? Okay, if you got to here, any questions from here to here, down to this? That's from a little bit. Or one line before it even. Let's look at that for a second there. Anything there in that? Okay, I just wanted to check. It looks like you're wondering. I just wanted to give you a chance to. Yeah, Yeah, basically, you multiply up and down by e to multiply up and down by the conjugate. But yeah, put a negative 8,000. Make it e to the negative 8,000 kt here. This is okay here too, right? This is okay if you leave like this. That's okay. This answer is here is okay. But if you want to write it in a little nicer form, you multiply up and down by e to the negative 8,000 kt. It basically turns into this then. Right. Okay. Now, I want to show you one thing. We're almost done here. Let me show this on the computer just to see the graph of it, see if it makes sense. Okay. So let me stop sharing here and share back. Okay, share up here real quick. I would have had plenty of time for this if it wasn't for that thing in the beginning. But okay. But anyway, let me show you this real quick. I won't do the slope field here, but basically, if you show the solution to it, can somebody read off what the solution was? It is like y equals that. It was 8,000 over 8,000 over 1 minus.
Or was it 1?
Was it 1 minus?
Was it 1 plus?
Was it? I don't remember. Plus. Okay, 1 plus, and then it was what 7999 e raised to the was it e raised to the negative kt? Was it negative kt? I can check if, or no k in it. I'm sorry, no k. Or was there k? Did I drop a k off of there somewhere? My bad. There should have been a K in there on that very last line on the solution there. I went down by the conjugate. Okay, that where I have e to negative 8,000 t at the end on that last line, it should be kt. There should be a k in there. So you see what I'm talking about? Yeah, that should have been there should have been a kt in there. Let me just, yeah. If I share back real quick on this. Almost done here. Wait a minute. Share back. Yeah, so see here. You can see it on the screen there. See the negative, where it sees negative 8,000 t, down it should be negative 8,000 kt. This part right.
Yeah.
Right
No, I
down
know
here.
what you're saying.
Should be a kt. I dropped the k off there. Should be a kt there. But when I do this in Desmos real quick, then, so if I go back here, stop sharing, share this back now. Almost got it. So it's e raised to negative kt. Negative. Now the k was that, what was that k again? The k was 2 over
799.
Okay, 2 over 7,999. And then I need a t after that. I guess kt, right? Oh, we'll see what becomes of this. I don't know. And, oh, no t's. It doesn't like, I need x's. I think that's it. Let's see. Try that. And why is it flat?
I want you to just zoom out just a little bit.
No. This is 8,000 over 1. Was it plus in my final answer? What was my, oh, there. Okay. 8,000 over 1 plus 7,999. Oh, and then there's I'm sorry, there's an 8,000 I missed there too. E to the negative k, 8,000 kt. So I need to times 8,000 in here. I think I missed that. Try that. There we go. Okay. So then if you look at the growth of it, see if we get a good window. Well, yeah, that's actually probably right though. It's going to go crazy. I get up to 8,000. My window. How do I change the window? Whoops. Open settings. There we go. Let's make this 0, and I don't know how many hours. I can't go that far. Say maybe 10. Or then let's say this is 0. Y max is say 8,500.
You just change this.
Yeah, there we go. Okay, so then this looks better. Where'd my 0 go?
Go back again.
Back to here.
Axis.
Oh, thank you. Show axis there. So there we go. That's what it looks like finally, right? So it starts off slow. We have 1 bacteria to start, and then it grows. You see the limit, 8,000 is the limit up here. So it grows fast, and then at some point it starts slowing down again. Okay, so that's the solution curve like that. So, yeah. Okay. Anyway, anything on that? So, okay. So we'll stop there, and you guys should get out of here now. Let's see. Okay. So, and